Hello and welcome back to Let's Code Physics. We have had some pretty good success with our wave function evolver so far. We have extended it to 2 dimensions. And again, 2 dimensions can mean you've got a single particle moving up, down, and left, right, or it can mean you've got 2 particles that are free to move along a one-dimensional axis. So what we took a look at last time was 2 charged particles moving along sort of like a one-dimensional rod. So you might imagine you've got 2 electrons trapped in a carbon nanotube or some kind of one-dimensional structure. And what we saw was that the expectation value of their positions kind of tracked along with each other to maintain this almost constant separation distance. The wave function had this interesting shape where it shifted some weight back and forth. There was kind of this canyon in between where the 2 were not allowed to be because there was this electronic repulsion. And that was really cool. But the Coulomb the Coulomb potential energy only gives you repulsion between like charges, or it only gives you attraction between opposite charges. So it's either going infinitely high or it's going infinitely low, depending on whether you've got attraction or repulsion. A more sophisticated potential energy is one we use for molecules. So for example, if you wanted to model protein folding, one of the ways you might do that would be through this thing called the Lennard-Jones potential, which models neutral particles or neutral molecules, clusters of particles, clusters of particles, where at a distance, at a very far distance, they're not going to have any effect on each other. But as they get closer, they start to attract each other. But when they get too close, they repel each other. So interesting thing I learned about protein folding. So mad cow disease, which has been, of concern recently in the last, decade or so, is actually transmitted by a misfolded protein. So it's a disease that is not transmitted by a bacteria or a virus, because in school I was taught that diseases are caused by bacteria or viruses, or at least infections are. But no, this is literally a protein that is misfolded, that when it goes into another life form, it causes the other well-folded proteins to misfold in the same way, and it causes this cascade reaction that causes the disease. It's scientifically speaking, it's really interesting. It's horrible, obviously, but it's a really interesting problem to have to try to solve. And so one way you can model this interaction between molecules and a protein is the Lennard-Jones potential energy. And the Lennard-Jones is interesting because it can be both attractive and repulsive depending on the relative distance of the 2 particles. So what we've got here is we've got set up the Lennard-Jones potential energy. Again, we're putting in a cap of 500 just to keep it from causing the thing to sort of go off the rails, as it were. So we are putting a cap at 500. We'll take a look in just a second at whether that's reasonable. But in order to define the Lennard-Jones potential, you've got to define 2 parameters. So when you graph this thing, it ends up looking like this. So this is the potential energy versus the separation distance between the 2 particles. So again, very far out, you've got this attraction, right? So when you think of a potential energy graph, you want to think of things as tending to roll downhill. So in this case, if the 2 particles are very far apart, they're going to tend to roll downhill toward each other until they reach this minimum, and then there's this very, very sharp uptake here, really an asymptote as you approach separation equals 0. And so they're going to roll back very quickly. So they're going to slowly approach each other and then, sort of knock back away. So the 2 things you have to specify for the Lennard-Jones potential energy is the depth of the minimum. You've got to specify how deep this dip is from 0, and you've got to specify where the dip is on the horizontal axis. So that's what we've got specified by Emin and Rmin here. We've got a depth of -10, and that's what I've got on this graph is a depth of -10, and a location along the r-axis of 1, so it's at -10 and 1 there. And basically, once you specify those two, everything else is taken care of, because the way the potential energy works is that you've got E minimum, so that sort of scales the whole thing vertically, and then R minimum scales the whole thing horizontally, because you've got R minimum divided by R and R minimum divided by R. And there's the first piece, that's that fraction getting raised to the 12th power, so that is this piece right here where it is repelling as you get closer and closer to 0. And then you have a negative Rn over R to the 6th power. It's multiplied by 2 to take care of the scaling and everything. But this is being raised to the 6th power, and it's a negative, so that's what's producing this tail right here. So at very low separations, the R to the 12th is dominating. At very high separations, the negative R to the negative 6 is dominating. And in between, they're meeting and creating this minimum. By the way, if that looks familiar, it's because that's the same general shape that we got back when we were constructing the root finder in space, where you had the attractive gravitational potential energy, the real potential energy, and then you had this effective centrifugal potential energy that causes the two things to repel each other. It's not the same math, because the other one was to the 2nd power and to the 1st power, but this one is now to the, to the negative 2 power and the negative 1 power, but this one's to the negative 12 and to the negative 6. But again, it's this negative in the middle that's producing that minimum there at R minimum. So again, we put the cap at 500. So if I change my scale here, again, I'm in GNU plot, which is pretty handy. You can see it took me several tries to get this to plot correctly. If I put this thing at 500, so you can see the minimum kind of vanishes. So 500 is definitely, high enough to go. And if I take a look at the location down here, I see that I reached the 500 mark at right around 0.7, so at 70% of the R minimum separation, which I think it's going to be pretty good, so that means we can get, 30% off of this thing and still be tracking the correct potential before we flatten it off. So imagine the red curve here just flattening off right there. That's what's going to happen in our approximation of the potential energy here that the computer can handle. And that's all I really have to change. I think I'll leave the initial wave function the same. So again, it's this Gaussian, this double Gaussian, or this two-dimensional Gaussian that's been displaced a little bit along the second particle axis. Is that the red one or the green one? I think that's the green one. And so what I'm going to do now is I'm going to run this. We should see kind of similar behavior to what we saw last time, only now, again, there's this minimum. So they're not going to get too close to each other. So again, along the x equals y, there's going to be this huge divide where they're not allowed to go. But they're not only going to be repelled from each other, they're also going to be attracted by the attractive part of the potential energy. So I'm just going to run this thing initially, and if it goes well, then I'll let it run overnight, and then again I'll speed it up for you, just like we did last time. Oh dear, overflow error, result too large. Okay. And when are you getting this result too large? It looks like it's in line 161. I may need to decrease the potential energy a little bit. Let's go to line 161. I'm guessing that'll be in the code itself. Okay. So then here's my question. Is it the psi current squared that's too large, the psi real current squared that's too large, or the psi fact that's too large? Surely if the psi fact were too large... Oh, you know what? The psi fact... Isn't that scaled by U max? Do I even need that anymore? Where does psi fact get determined? Psi fact is x max minus x min divided by psi max. Okay, so no, that's not determined by U max. That was previously, I was doing it that way. Let's see. Well, the U max is a problem, right? Oh, you know what? That is a problem because I was only dealing with this is the minimum of the two. It should still be the minimum. So why is U maximum... Why is U max turning out so large if it's being capped at 500? All right, so where does U max get determined? Umax equals 0. Umax equals maximum Umax in the absolute value of U. I don't think I want that to be absolute value anymore, although that shouldn't be making a difference. Let's see. Okay, well, the Umax got better behaved. I'm wondering, okay, let me double check my potential energy now, because my potential energy shouldn't be going higher than 500. And it shouldn't be going lower than 10, or the negative 10. Oh, you know what? Let's do that. Let's check U min as well. Let's check the minimum of U. So let's do the same thing here. We're going to say U min equals 0.0. Oh, no, actually, let's make U min equal to 500, since I know that'll be the maximum value. And Umax equals this, and so we'll copy this line. I had a shift and a page up or something. All right, try that again. Umax, all right. Home, copy, paste, there we go. So let's try this. U min equals this, and the beautiful thing is the minimum will work if it's negative. It'll just keep going more negative. Oh, but I need to print U min or else calculating it doesn't do me much good. Now does it? So let's do Umax, comma, U min 5. Okay, so that's disturbing because that should not be getting that low. That should be getting a minimum of negative 10, right? All right, let's check what I'm doing here versus what I'm graphing. Oh, that is not my code screen. That is my code screen. All right, let's go up to here. It never goes right the first time, does it? Minimum between that and that. Okay. Okay, so it is. All right, let's double check what we got here. Okay. So what I'm plotting here is 10. Oh, whoops. I set my E min to be negative 10. I flipped that thing upside down. Oops. Save. There we go. Why did I put a negative on that? Why did y'all let me put a negative on that? All right, let's try that again. Okay, cool. So that worked out better. Yes, max of 500, a negative of negative 10. You know what it was? I was thinking the minimum needs to be negative 10. I wasn't thinking that the minimum needs to be 10 below 0, and that's what I was doing there. Okay, well, all is right with the world now, I think. So there is our Gaussian. Again, we've got our rift kind of developing along the y equals x line, or along the red equals green line. Oh, that's kind of cool. We're getting these little ripples there. Is this supposed to be like that? Oh no, we're getting a little bit of wave motion over there. Okay. Well, cool. This seems to be behaving properly. Yeah, again, I've pinned things down along the side here. Actually, one of my alumni, who's currently getting his PhD and has far surpassed me in terms of computational prowess, offered a thought about why I was getting those ripples off of the edge there. He said, well, because it's a symmetric second-order differential equation, you're going to get in the solution you don't want, which is the exponential growth. But then when I pointed out, right, but it's only coming on one side, that one he didn't know how to do. So Krupa still waiting on an explanation for that one. Okay, so this seems to be behaving pretty well. So I'm going to keep an eye on this for another, like a couple minutes. And if all goes well, I will let this run overnight and then speed it up again. And we'll get to watch it unfold together. Okay, so I've reviewed the video and the results come out very interesting and come out very well. One of the first things to notice is that the wave function very quickly distributes itself primarily between quadrants 2 and quadrants 4. The significance of that, again, is that those correspond to the red particle and the green particle being on opposite sides of the of the one-dimensional structure that we've got in place. So if you imagine this as a carbon nanotube, they're on opposite sides of the carbon nanotube. And they kind of quickly become, kind of uniform across them. So I won't be commenting too much on the wave function itself. And actually, that's a good thing because, as we'll talk about in a couple minutes, I actually want to be able to get rid of that in the next simulation that we run. What you see again, just like we saw with the Coulomb potential energy results, these two expectation values track each other pretty well. In fact, they track each other more closely than they did for the Coulomb potential energy. Remember, with the Coulomb potential energy, we got all this noise in both of them, and we have some noise in these as well. So we've got some local jaggedness. But for the Coulomb potential energy, those were pretty independent of each other on the red curve and on the green curve. What we're going to see on the expectation values here is that they track pretty closely. When one tends to curve upward, the other one's going to tend to curve upward, and vice versa. So if you were to graph the difference between the two expectation values, you'd get a pretty flattish line. It seems to be a difference of pretty consistently about 0.08, I think it is. Let me double check on the scale. So about 0.02468. About a 0.01, about a 0.1 difference, So you get a pretty consistent difference of about 0.1. What we're also going to see is that they form a pretty regularly repeating pattern. Of course, any wave function is going to be composed of sines and cosines in a Fourier series. If you need a review for what a Fourier series is, go check out my lightsaber Fourier series video from just a couple weeks ago. But even in a Fourier series, you're going to have an overall period to the motion. And if you take a look at sort of the major peaks and major troughs of these expectation values, you end up with a period of about 1.1 seconds on the horizontal axis there. Not 1.1 seconds in video time, because the video time is going to take 9 minutes to go, about 2.5 seconds on the wave function. And of course, it really took it 9 hours to record. I'm speeding this up 64 times. But you get this nice regular period. Looking back at the Coulomb potential energy results, it's a lot more regular. It's a lot more repeatable, which, of course, also goes along with the fact that the two expectation values track with each other so closely. There's probably two reasons for that, looking at the differences between the Coulomb potential energy and the Lennard-Jones potential energy. One is that the repulsive part of the Lennard-Jones potential energy is a lot stronger than the Coulomb potential energy. The Coulomb potential energy grows like 1 over the distance between the particles as they get closer together, and the Lennard-Jones potential energy grows like 1 over the distance to the 12th power. So if you were to graph those, on a logarithmic scale, in terms of power, the Lennard-Jones potential energy grows 12 times faster than the Coulomb potential energy. So, that means that there's a lot stronger of a restorative force between the two. But also there's this attractive portion to the Lennard-Jones potential energy, the r to the -6, that is not present in the Coulomb potential energy, which of course is what gives you that minimum. And so I'm inclined to think that that minimum, that the fact that a system is going to tend toward its equilibrium point, which is a minimum in the potential energy, I'm inclined to think that that's the reason these two track so well together, except for the fact that their distance, average distance between each other, is about a 0.1, and I set the equilibrium distance to be 1.0. So it's a full order of magnitude lower than the natural length scale in the problem. If I had set the distance to be 1.0 and the distance between them ended up being an average of about let's say about 0.9 or 0.75 or even 0.5, I could say, okay, there's probably a 2 that gets divided in there somewhere, or 3/4, or rounding error or something. But this is a factor of 10. This is a full order of magnitude different, and that's kind of bugging me because I know that it should be proportional to the equilibrium value. Now, of course, another thing that could be causing that is the initial distance between them was about a 0.2 in the initial wave function. The red particle is not displaced. I'm looking it up now to make sure that I'm saying something that makes sense. Yeah, the red particle, the x is not displaced, whereas the y is displaced by 0.2. So that's probably what's contributing to this, just based on the numerology of matching up the orders of magnitude. And so what I'd like to do next, we got about 3 minutes left on this video, so I'd like to talk about what we're going to do next, is investigate this distance between them. So we're not learning a whole lot from the wave function anymore, and we really don't learn a lot by looking at the red expectation value and the green expectation value. What we're really interested in is the difference. And so what I'm going to do on the next episode is I'm going to set up the code to calculate just the expectation value of the difference between the red and the green. So red expectation value minus green expectation value minus red expectation value. Green is the one on top. And that way it'll produce just a single graph. We won't be worried about the red and the green, and it'll be a roughly flattish graph, right? Just like these two are roughly consistently different from each other. This is going to be a roughly flattish graph. And I want to iterate that over a couple things. I want to produce a family of curves for that over a couple things. One is I want to change the R-min, that equilibrium distance, and see whether the difference in expectation value scales with the R-minimum, that difference. I also want to change the amount by which the initial wave function is displaced. So that 0.2, change that to some different values and see how the expectation value difference changes with that. And so if I'm right about the R minimum, we should see a significant change there. If I'm right about the wave function displacement, we should see a difference there. If I'm wrong about one of them, then we won't see a difference. If I'm wrong about both of them, then I really have to go back to the drawing board. What else do you think I should try? What else do you think I should try changing to look at different outcomes of the graph? And so all we're going to have on that, let me know in the comments below. All we're going to have in that video is going to be I'll be setting up the code and then the expectation value graph. I'm not going to sit there animating wave function after wave function because, number one, that's not going to be that interesting to watch. But also, hopefully then I can get the whole thing done running over one night instead of running over an entire week, because I do kind of need my laptop for other purposes, like doing ticket to ride route generators. I'm referring to another currently ongoing series on Fridays on this channel. So this video's got about 30 seconds left on it. I do want to thank you for watching. I will close out with the last little bit of animation there. You can, take whatever measurements you want off the graphs. Again, thank you very much for watching. I will see you next time. Bye-bye.